Okay, so let's quickly recap what we were doing. We were doing correlated strategy equilibria. We said that if SDSC exists, correlated strategy will be the same as DSC. It does not make any sense to study about correlated strategy equilibria when the SDSC or WDSC exist. But what we are interested in is we are interested in asking suppose there is no SDSC or there are multiple correlated strategy equilibria, then which correlated strategy equilibria should the mediator choose in our traffic control game. In the traffic control game, at least it is clear that the correlated strategy equilibria which make more sense in some way is to give 0.5 probability to stop comma go and 0.5 probability to go comma stop, at least in that game, right. So, we want to basically define some of the nice properties that these correlated strategy equilibria should satisfy, right. So, this is our goal, that if there are multiple correlated strategy equilibria, then which one should I implement? Is it okay? Okay. So, let us try to understand from the two-player game, okay, and this game is known as two-person bargaining problem, okay. So, this is two-player or two-person bargaining problem, and this problem, it will make sense once you understand the problem, but let us try to understand this problem from a different perspective. So, there are two people, two-person bargaining problem consists of two players and this particular pair which is capital F comma small v. Okay. What is capital F? Capital F is the set of all feasible solutions. How these feasible solution look like? We will discuss it later, okay. But it has some set which is set of feasible solutions and it has some V which is a vector which is V1 comma V2, and this represents some kind of disagreement point among the players, okay. So, this basically represent the disagreement point giving the players payoff if negotiation fails. We will look into it little bit, okay. So, what is two-person bargaining problem? Why this name is? It basically means there are two people who are basically bargaining with each other. So, if you see with respect to cooperative game theory also, correlated strategies also, right. So, there are people who wants to cooperate with each other, but when they are cooperating, they are bargaining with each other. What should we do, right? So, imagine in that way. So, there are two people who are bargaining with each other. We will cooperate, if you do this, I will do this, something like this, okay. And what disagreement point says is the similar thing to the contract signing thing. Disagreement point says that this is the default value I will get if the bargaining fails, okay. So, similar to the contract signing game in our prisoner's dilemma example, if you do not sign the contract, if the bargaining is failing, I will confess. So, in that case my disagreement point was 1 comma 1, make sense? Perfect, okay. Now, typically V belongs to the feasible set, and in this case my feasible set will be what? Feasible set will be all possible utilities which can be achieved through the correlated strategies. So, what I am asking? So, what I want from this feasible set, I want to find a good solution. I do not know what is good solution for now, but this good solution will emerge from this feasible solution. Okay. So, because I want to find a good solution among all possible correlated strategies, my feasible solution will be the utilities corresponding to the correlated strategies. Does it make sense? So, in our earlier case, and not only correlated strategies, it would be correlated strategy equilibria. In our traffic game, what was the feasible set? It was all possible correlated strategy equilibria which gave beta probability to stop comma go and 1 minus beta to go comma stop, okay. And then it has some disagreement point, okay, and disagreement is similar to the maximum value of a player, and basically what I am looking for, this good solution should satisfy the property that the individual thing that I am getting should be greater than equals to V1 and it should be greater than equals to V2. Make sense? Perfect. Okay. So, given a correlated equilibria alpha, what you can do is you assign x1 to u1 alpha and x2 to u2 alpha, and you define your set, the feasible set F, to only those corresponding to only those alpha which are the correlated equilibria. Okay? And what I want some good point out of it. Okay? Okay? This is the question that we want. Is the question clear? So, I have lot of correlated strategy equilibria, I want to find some good point here. Now, the question is, how do I define the goodness of the solution? Okay. So, how do I define the goodness of the solution? These are some of the properties that once I explain it to you will make sense. Okay. So, a goodness of the solution will be basically defined by these 5 properties, and let us see what these 5 properties says. But before that, suppose these 5 properties are satisfied, if there is a solution which satisfies all these 5 properties, then this solution is known as Nash bargaining solution. Okay. And my main result says that there exists a unique solution which satisfies all these 5 properties. So, now you were looking for good point, there will not be multiple good points. There will exist a single good point which will satisfy all these nice properties, and that good point is termed as the Nash bargaining solution. So, out of those many solutions, you could possibly look into the solution which satisfy all these 5 properties, and it will be unique. Make sense? Perfect. Okay. So, what these 5 properties says, let us try to understand. Okay. The first property is called the strong efficiency. Okay. Strong efficiency is similar to the Pareto optimality. Have you heard about Pareto optimality in mechanism design? Okay, good. So, what is a Pareto optimal solution? A Pareto optimal solution is a solution such that there does not exist any solution which gives lesser utility to all the players, right. So, basically there does not exist any solution such that xi is greater than equals to this good solution which is satisfying the efficiency, and xi is strictly greater than this solution for some I. Is this definition okay? This is simple Pareto optimal definition. So, that means what you are saying is, suppose the set that I am looking for, this is my F, okay, okay, then which are the points that satisfy strong efficiency? Sorry, which will be here? This one, this line. This line will be basically all the points that will be satisfying Pareto optimality. So, any solution on this line will be satisfying strong efficiency. Sure? Okay, good. Okay. This is individual rationality. You also want individual rationality to satisfy. That means the solution that you are looking for should be at least better than disagreement point. Perfect. The next property is called the scale invariance property. What is scale invariance property? Do not look at math for now, just understand the intuition. Scale invariance is simple. Whatever your solution, whatever your feasible set was, capital F, right? What you are doing, you are basically scaling this complete feasible set by something. Okay. So, the point here will basically correspond to some point here with some parameters lambda 1, lambda 2, mu 1 and mu 2. Okay. So, x1 comma x2 here would become lambda 1 x1 plus mu 1 comma lambda 2 x2 plus mu 2 here. Each and every point will be scaled by these fixed parameters. Okay. So, you are basically scaling this space to something else, transforming. Okay. Then what should happen? If there exists a solution which is this, it has to be Pareto optimal, so it has to be on this line. suppose this is the best solution that you find, then this best solution should correspond to the scaled version of the solution here. Okay. So, if x1 comma x2 is the solution here, then lambda 1 x1 plus mu 1 comma lambda 2 x2 plus mu 2 should be the solution here. This is called scale invariance. That means, when I am linearly transforming my entire space, the solution is also transforming by the same linearity.
Physical intuition behind this
So basically, if you have a game, okay, and what you do, you basically increase each and every number by, let us say, multiply everything by 10. Then whatever solution you are getting should also be multiplied by 10. It should not be some arbitrary number. Okay. Okay. The third property, again you would have seen this. Have you seen this? Arrow's impossibility theorem. Yes. Okay. So, this is independence of irrelevant alternatives. What does it mean? It means that if I remove some of the alternatives which does not matter, then my solution should not change. Okay. So, if I had this entire F, and if I restrict myself to this set G, which is a subset of F, okay, then what should happen if the solution belongs to G, okay, if I had this entire space F and my solution is this. Now, I consider another subset G which is this, and the solution is still in G. Then even if I say that my feasible set is not F but only G, then also the solution should not change. So, these points basically are irrelevant for this solution. Does it make sense? Okay.
Does this only hold for a Pareto optimal solution, or is it true for any solution?
I mean, you can still, I think you can easily come up with a solution which is satisfying IIA property and not Pareto optimal. So,
Because the fact.
No, so imagine that you have the solution here which is not Pareto optimal. Then also you can enforce a property that if I stick to this thing, then also solution should not change. So, these properties are independent of each other.
Yeah, but we want a solution
which is Pareto optimal. Yeah.
So that's why we are only looking at those.
So, we are actually looking for the solution which satisfy all the 5 properties.
Obviously, the Pareto optimized is the first property.
Exactly.
Okay, so this one can be interpreted as saying like, okay, take an optimum solution, let's say, in this case Pareto optimal, look at a subset of the feasible space that contains that optimum solution. Then that optimum solution, which is optimum for the whole set, remains optimum for the
smaller space also. Yes, exactly.
They don't have a local better solution. Locally don't have a better.
Okay. That's the first thing. Now, another property is called the symmetry property. What is symmetry property? If I have a symmetric game, that means my V1, my disagreement points are exactly same, and if x1 comma x2 belongs to the feasible set, then x2 comma x1 also belongs to the feasible set. Okay. Our traffic game was a symmetric game. Okay. Then what it is saying is that whatever the solution, whatever the point you have that you are looking for, this two also should coincide. That means, utility that the first person is deriving should be equal to the utility of the second person, because it is a symmetric game. Does it make sense? So, all the 5 properties in some say seems logical, these are the axioms, and now what you are looking for? You are looking for a solution which satisfies all the 5 properties. Okay. And that solution which satisfy all the 5 property is called as the Nash bargaining solution. Okay. And this is a theorem which says that for the 2-person bargaining problem, there exists a unique solution that satisfies all the 5 axioms, and this is nothing but x1 minus v1 into x2 minus v2. This is also called Nash welfare in fairness literature.
Are we assuming that there is a unique disagreement point?
Right now, yes. I mean, max-min value will be unique, right, by the very nature of it.
There can be multiple points that attain that value.
But the value itself is unique. Yes.
And that's all we need.
Yes. Okay, so this is called the Nash welfare solution in the fairness literature.
So is f prime saying some monotonic property?
No, f prime is simply saying that you are restricting yourselves to disagreement.
Yeah, so every point beyond the disagreement, only coordinates beyond above disagreement.
Because you wanted to satisfy individual rationality property, therefore you need to restrict to only the points which are giving utilities beyond the disagreement point. Make sense? Okay. The hard part is to prove this. Okay. The easy part is you can easily prove that this particular solution satisfy all the 5 properties. That's easy. That's not difficult. Okay, just check the definitions, write it, you will get it. Okay. The tricky part is to prove the uniqueness. How do you prove uniqueness?
Assuming there is another.
By assuming there is something else which satisfies all the 5 properties, but it's not this. So then by using this thing, you can actually come up with some nice lambda ones and mu ones such that it basically violates one of the properties. Okay. I don't think I will have time to prove this, so because I want to do shapely value at least. So let's move. Okay. Is this okay? Proving that this satisfies 5 axioms is not difficult. Okay. The other way is slightly harder. Okay. But I would still think about it. Okay. Those who like maths. Okay. I guess we can skip it, and I want to start something new now. Okay, so everybody with me so far? Good. Okay, so now what we have done is we have this nice concept of correlated strategy equilibria, and we understand about the good point when there are 2 people. But what if there are more than 2? Then what happens? Okay. So what I am looking into is that what happens instead of 2 players if there are more than 2 people. By the way, you can easily extend your Nash bargaining solution definition to more than 2 people. So in the Nash bargaining solution, what you had, you wanted to come up with x1 comma x2, which maximizes x1 minus v1 into x2 minus v2, right. If there are 3 players, what will you do? Into x3 minus v3, and so on and so forth, right. So Nash bargaining solution is not, I mean, it's difficult to compute, but at least definition wise it makes sense. Okay. But does it really make sense? Okay, this is the question that we want to ask. Is the Nash bargaining solution is a good solution when you have more than 2 people? This is the question that I want to ask. Okay. So if there are 3 players, you want to divide $300 among them. Okay. So the feasible solution will be all such x1, x2, x3, because this define the utility such that x1 plus x2 plus x3 will be less than or equals to 300, right. And v, let us assume they are 0. So everybody is happy as long as they are not paying anything. Okay. So Nash bargaining solution will maximize this, which is maximize x1 into x2 into x3. It is easy to see that the Nash bargaining solution will give 100 comma 100 comma 100. Seems fair, right. I mean, everybody gets equal, seems to be good. Okay. Now let us see this. Okay. So in order to understand this, consider the exact. So when we are talking about bargaining, right, a good thing about bargaining is people do have some bargaining power. Yeah, right. Some people will have more bargaining power, some people have less bargaining power. So I want to explain that. Okay. So, in the 3 people example, when you are dividing the $300, imagine that there is a father who is leaving this $300 and it needs to be divided between 3 brothers. Okay. And initially what father is doing, you can divide whatever you want, but whatever division should happen, you should all agree on this. Okay. So, because father is making everybody agreeing on something, everybody has the equal bargaining power. So, that is where 100, 100, 100 makes sense. Okay. Now, consider another thing. Let us say there is a younger, very small youngest brother, and father does not trust him, and he says ki you divide whatever you want as long as the 2 brothers are agreeing. The other two brothers are agreeing. Then obviously these 2 other people have more bargaining power as compared to third person. Then why will these 2 brothers will give any money to the third brother? They shouldn't. Again, we are doing game theory, rational and intelligent. I want to maximize my utility. I don't care what my brother does. Okay. So, then it does not make sense to give 100, 100, 100. In this case, since 2 brothers are sharing the bargaining power, it will be 150, 150, 0. Fine? Perfect. This is not Nash. Nash bargaining solution is 100, 100, 100. But what I am saying, if the rules are changing, the solution that makes more sense will change. Okay, we want to capture them. Let us take another version. Now, what father is saying is that I trust more the oldest brother. I am happy as long as any 2 brother which include the eldest brother is happy, I mean agrees. Okay. So, in this case what will happen? The utility will be xi if either 1, 2 agrees or 1, 3 agrees. Okay. In this case what will happen? 2 and 3 will have equal bargaining power, but first person will have the highest bargaining power. So, in this case what will happen?
Whoever takes the least.
It will keep almost 99.9999 whatever percent to himself, because it can always say, this person I can go and make more money. So, right. So, in this case the Nash bargaining, in this case the solution that makes more sense is 300, 0, 0. Okay. Finally,
In this 0, 0, so both of them say no, we are not coming with.
then everybody gets 0.
So this one can't. Like, okay.
It converges to 300, 0, 0. It's similar to divide the dollar game, right? Okay. So, now version 4 is basically you do the majority voting. Then what will happen? Then it never converges, right? I can always jump around. Okay. Okay. Hanji. Nothing happened, like it doesn't converge. So, whatever we agrees on, the person can always switch to the other coalition. That is what I am talking about. So, now every coalition is 1, 2, 1, 3, 3, 2. Okay. So, no coalition is better than the other coalition. I can always just jump around. We do not have a solution here. Okay. So, what I am saying is Nash bargaining solution may not make much of a sense when you have such things in your game. Okay. In order to basically define proper rules of the game, now the next concept that I want to basically tell you is called the transfer utility game, and we will understand those examples using this game. Okay. So, what is transfer utility game? In the transfer utility game, what we assume is that there is a valuation function which basically maps any subset to a real number. Okay. Intuitively imagine it as the following. if the subset of people basically agrees to come together and work together, then the mapping which it is mapping to, it denotes the worth of this coalition, how much value they can produce when they come together. Make sense? Okay. So, there is a money component here that players can freely transfer among themselves such that any player's payoff increases by 1 unit for every unit of money. Okay, let us not go into this. Okay. This we have already done, this we have already done. By default, we will assume that V of phi equals to 0. Okay. So, now the main issue in the transfer utility game is that how do I define the valuation function? Okay. So, let us take an example, how do I define the valuation function in all the version of the divide the dollar game. Okay. So, my first example was when everybody has to agree. So, then when I am defining the TU game, transfer utility game, I need to define the valuation function for each and every possible coalition. Okay. By default, I will assume V phi is 0. Okay. So, in this case V phi is 0, V1 will be 0, V2 will be 0, V3 will be 0, V12 will be 0, V13 will be 0, V23 will be 0, but V123 will be 300. It means that only if everybody comes together, then only they get the worth of 300, otherwise everybody is getting 0.
V123 is arbitrary 300, like do we need to keep it 300 or just maybe say 1? Like, we are only comparing.
It has to define, so because you are dividing $300, then it has to be 3. So, it's basically giving you the total worth that coalition is giving, and in this case if all of them agrees, they are getting $300. So, this money component is there.
But it won't matter if it's 300, 1 or whatever, because this is.
I mean, you can say for the scaled version, but if you don't have V12 equals to 0, then it will matter. In this case it won't, but otherwise in general it will matter. Okay. In version 2, what will happen? In version 2, what will happen? V12 will be 300, V123 will be 300. So, in this case V12 will be 300, V123 will be 300, everything else will be 0. What will happen here?
V12 and V13, V123 will be 300.
Good. Okay. Here every pair will be 300, along with V123 will also be 300. So, we understand the how do I have the valuation function in the transfer utility game. Okay. Now, you may ask, it is a valid question, although you haven't asked so far, matlab it seems to be a hypothetical example, right, dividing the money among this thing, but it also happens, for example, logistic game. Okay. People do have more bargaining power based on where they are situated and what are the characteristic of them, right. For example, consider a logistic game where the idea is simple, you want to basically, you want to move something from S to T. Okay. And if you successfully move something from S to T, then it fetches a revenue of 100 units. Okay. The thing is that these roads which leads from S to T are basically provided by some service providers, and these service providers could be either 1, 2, 3 or 4. Okay. Each of the service provider for providing the service from one node to the other also incurs a cost. Okay. And that is represented by comma. So, 1 comma 10 means from S to A, service provider 1 provides a service at a cost of 10. Does it make sense? Okay. And if you have to really transport something from S to T, what would you like to do? You would like to basically choose the path which has the least cost. So, in this case least cost will be SCDET, right. So, it will be 15, 10, 20, 35, this would be the least cost. Okay. Now, the question that we are trying to, and this would be the total cost, and then you will divide it, whatever it is that we are looking for, but we still need to define the TU game for this. It is a cooperative game because the service providers should cooperate with each other to transport the good. Do you agree? Okay. So, now I want to define TU game. So, how do I define the TU game? I need to define the valuation function for each and every possible subset. Okay. Yeah.
The service providers are the agents, and if they don't cooperate with each other,
No.
a person they don't get any revenue.
Right. So, the idea that I am going towards is the following. So, suppose they achieve something, then how much, like for example, divide the dollar, what should you give to each people? Like how do you define the division?
It is already decided, right?
No, that is the lowest cost. When I am saying you define the TU game, you need to define that valuation function from all possible subset to the real number. In this case, it will be cost function.
But for each edge, the service provider is same, right?
No, it is different. It is mentioned in the figure. So, what I am asking is, instead of valuation function, I have a cost function here. So, what I am asking is, you want to define a cost function which is taking any arbitrary any subset to a real value. Okay. In order to do that, you need to do C of 1, C of 5 will be 0, C of 1 is equals to what, C of 2 is equals to what, C of 3 is equals to what, and so on and so forth, right. So, you need to define for all possible subset in order to make it a valid TU game. Okay. Now, instead of writing this, we will do some smart tricks. Okay. So, we know that every coalition will have a cost of infinity or whatever it is. Okay. So, valuation of 0 if it does not have the person 4. So, valuation of okay, I can define V because I have 100 units, sorry. Let us not bring cost into picture. So, basically if they reach from one place to other place, I am dividing 100 units from to the agents, sorry. Okay. So, if there is no 4, then everything, nobody gets anything. So, every other coalition which does not have 4 will be 0. Okay. Secondly, 3, yes.
What does that 4, 0 mean there?
So, it is fourth service provider with cost of 0, he is giving the service free. Okay.
Not free, but it costs him 0, right?
It costs him 0, yes.
It is free, why would he?
No, it costs him 0, yes, because you will give something to him, he is the most important person. Yeah. Okay. So, next thing is basically now what you want to do, you can also skip all those coalition which does not have 3 and 4. Sorry, 1, either it should have 1 or it should have 2.
Yes. Otherwise, the goods can't exit.
Huh. So, 3, 4 also gets the valuation 0. Okay. So, now you are looking for either 1, 3, 4, 2, 3, 4 or 1, 2, 3, 4.
2, 3, 4 can't.
But 2, 3, 1 also is needed, otherwise 3 can't.
So, 2, 3, 4 is not possible because 1 is needed. So, now you have only 1, 3, 4 or 1, 2, 3, 4.
Yes.
1, 2, 4 also.
1 to 4.
So, 1 to 4 is okay. So, 1 to 4 you can define and 1 to 4 will be 100. Okay. Similarly, what we did 1, 2, 3, 4, 1, 2, 3, 4 is this part. So, that would also be 100.
He should be subtracting the values, right? 100 minus 15 and 40.
I guess that you will do after you are dividing the word. That will come in the disagreement point,
I have a question.
not in the valuation.
But same subset can provide a different valuation, right? But we will give some unique valuation to each subset, right?
Yes, you are looking for the valuation. That's why I'm saying. So you don't define cost in the valuation. You are simply giving 100 units. Cost you will bring later.
Yeah, I agree, but like if we go
So
for
same subset, if you can actually take two parts for the same subset, okay, then the total worth is still 100. Which part they take doesn't matter, at least in terms of the valuation function as of now.
So the division of that value 100 will be different via different parts, but
The-
still dividing 100.
Still dividing 100.
Like here you have an example, S, A, B, E, G.
So for example 1, 2, 3, 4, right? Every possible path is giving the total thing. Okay, then basically you assume they take the shortest path to divide, but that's a different question. Okay. Okay. So before doing that, I want to basically tell one of the important properties of the TU game. Okay, two properties actually. One property is called as the monotonic game. What is a monotonic game? Monotonic game is basically saying if you make more people cooperate with each other, then the value function can only increase. So earlier was the monotone game, right? So VC is less than or equals to VD for all C subset of D. Okay. The super additive game basically says that V of C union D should, for any disjoint set C and D, V of C union D should be greater than or equals to VC plus VD. Okay, intuitively what does it mean? If C and D would have worked independently, then the total worth they are getting should be less than or equals to if they would have worked together. So it is incentivizing people to come together, okay, for any C comma D which are disjoint set. This is important. The convex set, basically it says that this is also the definition of supermodularity. It says that V of C union D is greater than or equals to VC plus VD minus VC intersection D. Just a definition. Okay. This definition is equivalent to this definition, again not difficult to prove, is that what it is saying is if you basically try to add an agent I to a larger set, then the marginal contribution of agent I to a larger set will be more than the marginal contribution of I to the smaller set. Submodular is the reverse. In the submodular function, the marginal contribution to the smaller set is bigger than the marginal contribution to the bigger set. Okay. So, these are the two definitions of supermodular and submodular. Yes.
Definition of convex game captures super additivity, right?
No, both of them are both of them are equivalent.
No. I'm talking about this.
Super additive and convex.
Super additivity is a some particular for C intersection D is right. So it can be used in convex game also.
So, the question is, does super additive game implies convexity or convexity implies super additivity?
Convex implies super additivity.
Huh?
super advertised convex.
For additive is
Oh. Convex game they do super additivity.
Sorry?
It's just a special case of convex game, right? Super additivity.
Super additivity is a special case of convex game. Okay.
When C intersection
So, every convex game is a super additive game.
Every
Every
super additive game is a convex because their C intersection D is fine.
we have a special condition for the super additive game, which is
Is V always positive?
No, so if some game is convex game, that means VC union D is greater than or equals to VC plus VD minus VC intersection D. This is satisfied. Okay. Now you consider any two subsets C and D which are disjoint. If these two sets are disjoint, because the game is convex, it will satisfy VC union D is greater than or equals to VC plus VD.
So
That means all convex games are superadditive games.
Where C intersection D is not phi, that is still a convex but not superadditive.
I think superadditive gives a subset of convex games.
You just added one condition to convex to make it superadditive.
Every convex is superadditive.
Every convex game is superadditive.
But every superadditive is also convex.
So suppose a game is convex. How do you prove how do you prove a convex game is superadditive? Suppose a game is convex. Okay, that means it satisfies this condition for all C comma D subset of N. Okay, now if you consider any two disjoint sets, okay, this is phi, that is 0. So it satisfies VC union D is greater than equals to VC plus D. So by very definition, every convex game will be a superadditive game. This is fine. Does this happen? Not necessarily, because this condition is satisfied only for those subsets which are disjoint. But which, if the sets are not disjoint, you can easily come up with an example, this condition is not satisfied. So you can easily come up with the condition, this is satisfied but this is not. It's easy to see that every convex game is a superadditive game.
What is the intuition between this definition of convex?
So things become slightly easier. So for example, when we talk about submodular and supermodular, what we are trying to do, so these are combinatorial function. Okay, so you have the evaluation function which is combinatorial and you are trying to find a solution. Okay, if you have these kind of characteristics, then the algorithms, some of the greedy algorithms work with a nice approximation ratio. I don't know if you are familiar with the submodular optimization. Are you familiar with that? So if you have a combinatorial problem and let's say the function that you are trying to optimize is submodular, then what you can do is, so it's a what is combinatorial optimization problem? You are trying to find a subset S which maximizes something. Okay, and this maximization of something is a function which is submodular. Okay, then what you can, it's a nice theory. Then what you can do is, the way you basically come up with the optimal subset is the following. What you do, you pick up a person which is best in itself. Okay, you put this person in your set S. Okay, now when you want to pick the second person, you basically see which is the next person which is doing better with this person that you had already chosen. Okay, you choose that, and suppose you want to choose some people, you basically choose greedily. So what are you doing? Every time you are basically choosing which person is doing best with the existing set. Now this is not the optimal solution, but this is almost optimal solution. This gives the approximate ratio of 1 by E. Okay, so these characteristics are really nice to have because they give you some solution. I mean, similar to yesterday, I don't know if you attended yesterday's talk. Yesterday also we did a similar thing in smart grids, right? So you define a characteristic of the solution so that it becomes better for you to find the solution. Okay, perfect. And we will see why. This is pretty good property to have. We will see this. Okay. So in TU game, what you want to do, again you want to do the same thing. So you had the feasibility set, okay, you have some valuation, and what you want to do, you want to divide this valuation among the individual agents. So in n people game also, you are looking for a solution space which looks like x1 comma x2 comma dash 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 to xn. That means what individual people will get. Okay, and so now I am trying to find the solution. I am trying to find the answer to the question which solution will be the best. Okay. So let us try to understand some of the properties. Okay. The first property is called the individual rational. What is individual rationality? Now I don't have a disagreement point right now. Okay. So what is individual rationality? What is value? So when we define the value function, what does it mean? It is basically defining worth of a coalition. right? So, individually rationality, what should it mean? If I am getting, let us say, xi unit, then it should be at least better than what I would have got when I would have worked alone. Okay. So, that means xi should be greater than or equals to vi. This is what it means. Okay. What is coalitionally rational? We are talking about this coalition, right? When it is good for me to work in a coalition. It will be better for me to work in a coalition when the individual payoff that I am getting by working in the coalition has to be at least as much as the worth of the complete coalition. This is called the coalitionally rational. Okay. Collectively rational means I am not pumping any more value. That means this sum has to be the equal to the worth of the entire coalition.
Can you again repeat the second one?
This one, coalitionally rational means if I am in a coalition, okay, then the total worth individually that we are getting, okay, it should be at least as much as whatever is the worth of this coalition. By the way, coalitionally rational, nothing.
The reverse, right?
Sorry.
Second property. The value of the coalition is greater than the sum of the people who they can work individually, right? Even though they are in coalition.
I can give 0 even if the worth of the coalition is $300. If I give 0 to everybody, then it doesn't make much of a sense, right? So, individual payoff that they are getting should be better than whatever the worth is. It should be divided kind of a thing.
So what is
Allocation. It's a
Allocation, yes. Yes,
So
please.
I guess what's the motivation of? Am I trying to say that it makes sense for players to work individually, right? Like this allocation is good for players because it is all of them together under this allocation is going to be guaranteed to be at least as much as the value of under any coalition.
No, what I am saying is if I consider worth of the coalition, let us say worth of the coalition is $300, then this worth of the coalition should be divided to the people who are participating in that coalition.
Yes.
I mean whatever worth is coming, it should be divided. They may get some extra, but उतना तो मिलना ही चाहिए अगर मैं सबको प्लस कर दूँ. So if this coalition is getting 300, then individual people who are working in this coalition, उनका whatever they are getting has to be at least 300. मतलब whatever worth, जैसे अगर मैं काम कर रही हूँ, so imagine you are bringing a project, whatever money I am bringing the project with the coalition, okay, that entire project money should be distributed. There should not be third person who is taking some part of the money.
So then am I trying to say that this point X represents a good solution?
Yes, something like that. So this we will
Hence
see.
has all these properties.
Yes.
If the second inequality satisfies equality, let's say, that means the summation is equals to value of the coalition. What will motivate an agent to form a coalition, to be in a coalition then?
It will be, right, because VI could be completely different from XI. Oh, you are talking about everything satisfy with equality.
Yes.
So you are talking about this also satisfy with equality.
No. If that doesn't satisfy equality.
Then obviously it's better for me to be in coalition, right? So imagine, understood?
And what is the case when sum of xi will be greater than this? Because in every case, if the valuation is 300, only 300 will be divided by the people in the coalition now. Nobody is giving extra to the coalition just because it.
So it has to be for all C, right?
Yeah, but it will hold equality for all C's.
I think you can come up with the example. Let me think. Okay, I think we will see some example. Yeah.
Can I ask some? So
Yes.
is this X, this particular solution, are people over here allowed to get extra money, like from outside of the
That's
value?
why we are defining these three. So because they are not getting extra money, therefore we need this to be equals to Vn.
But they can get money from other coalition and split it in another coalition.
So the example, sorry, I was still thinking about his example. The example that we were talking about, imagine 1 comma 2 has to agree. Divide the dollar game. Okay, so you are saying x1 plus x2 is equals to 300. So they were getting 150, 150, right? But v1 was 0.
Yeah.
Okay, so in this case x1 was 150 but v1 is 0. So it is strictly inequality.
Yeah, I'm talking about the second.
That's okay, but you can expand it to the other. So I'm talking about C was 1 comma 2 and individual one is 1. So you can take 1 comma 2 comma 3 comma 4 and come up with an example. It's basically C, for some C it will satisfy with equality, but for other C it can satisfy with strict inequality. In this example, my first C is 1 comma 2 coalition and the thing that which is not satisfying with strict inequality is 1. You can just extend this example. Yes.
Same example, we can take C to be singleton 1.
Yeah, that's what I'm saying.
Basically, it's just the second one, you are writing it out as a special case.
Yes.
So 1 comma 3
Slack?
in that case.
See, the slack that you are cutting is actually not for that, but I think the doubt comes because, okay, I take a particular coalition that's giving C 300.
Yes.
Then thinking in terms of that, okay, that 300 has to be, split equal or whatever.
So for some coalition, yes,
Yeah,
it is
but then
splitting
The
equal.
slack is coming because, you are going through all other coalitions.
Exactly. For that,
Basically,
it can be
yeah.
strict
The
inequality.
easier cases where you don't even cooperate with anyone, you actually get 0 if you are individual.
Huh.
But then the slack comes because when you start actually cooperating, you get something more and then that's okay.
Exactly. Yes.
Good.
Got it. Perfect. Okay. And this leads to an important concept which is called the core. Okay. So the definition is simple. I basically say that set of all payoff allocations that are coalitionally rational and collectively rational basically forms a set which is called the core. Is it okay? Just a definition. So basically you find all such payoff allocation which satisfy these three properties. I am not considering individually rational in the definition because coalitionally rational implies individual rationality. So if these two properties are satisfied, all those payoff allocation which satisfy these two properties forms a core. Okay. So basically what you are looking at is we do understand that a solution should satisfy these properties. So basically what you are looking at, you are looking to satisfy these three properties. That means you are looking for a solution which belongs to core. Do we agree? Perfect. So this is the definition of core. Okay. Now why core is important, this will be clear from the blocking coalition. Okay. So suppose there is a solution X which satisfies this property and this is not in core. Okay. Suppose something is basically what you have collectively rational but is not coalitionally rational, that means there exists a C such that summation over xi is less than Vc. So you were asking, right, why greater than equals to Vc makes sense. Then what can happen is because collectively they are getting less, so because they are getting less payoff allocation from the solution, what they can do is they can basically make a coalition among each other, get a worth of Vc and distribute themselves. Okay. And such a coalition is known as the blocking coalition, because instead of going to the solution that you are proposing, they would basically form the coalition together and can do better. Okay. Core is closed and convex, again prove it. Yeah. Sushmit, question? Okay. However, the issue is core can be empty. Okay. Can you come up with an example where core is empty? Sorry?
The version 4 of
The version 4. So prove that the version 4 of the game, it does not have any core. So when majority voting, so you wanted x1, x2, x2. So basically the equations that you will get is x1 plus x2 should be greater than equals to 300, x2 plus x3 should be greater than equals to 300, x1 plus x3 is greater than equals to 300. None of the payoff will satisfy those properties, and you also want x1 plus x2 plus x3 equals to 300. All these 4 properties cannot be satisfied, you can easily prove it. However, and that's the beauty, the core of a convex game is never empty. That's why convex games are important. Core of a convex game is never empty. Okay, let me tell you what will be in the core and leave it to you to prove that it is in fact in the core is the following. So what I am going to do is the following. Suppose I have a TU game which is a convex game. I will give you a payoff allocation which will be in the core. Okay. The thing that I will leave out is proving that it will be in the core. I am just going to give you the payoff allocation. Okay, and it is your responsibility to prove that it is in the core. Is the question clear? Okay. So I have a convex game. I want to find x1, x2 dash 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 to xn. Okay. What I will do is I will assume that I have the indexes on the agents. Okay. So the agents are number 1, 2, 3 dash 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 to n. I have these nice numbers on the agents. Okay. What I will do is I will just do the marginal contribution to find the payoffs. So my x1 will be nothing but v of 1 minus v of phi. This is basically 0, so this will be nothing but v of 1. So x1 will be v of 1. Okay. My x2 will be v of 1 comma 2 minus v of 1. This will be my x2. Okay. My x3 will be v of 1 comma 2 comma 3 minus v of 1 comma 2. In general, x of I will be v of 1 comma 2 comma 3 dash 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 to I minus 1 comma I minus v of 1 comma 2 comma 3 dash 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 to I minus 1. This would be my exercise. Now it is easy to see that summation xi equals to v of n, telescopic sum. Okay. So summation of xi is equals to v of n, it is easy to see that. What is not easy to see that this belongs to core. How do you prove this belongs to core? In order to prove that it belongs to core, what you need to do? You need to basically take an arbitrary coalition C, which have some agents, because we have already numbered the agent. Let us say C has the agents I1, comma I2, comma dash 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 to IK. Okay. What you will have to prove? You will have to prove that xi1 plus xi2 plus dash 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 2 plus xik will be greater than or equals to v of c. This is what you will have to prove. Okay. This I have already written. Okay. In order to prove this, you will have to use the convexity property. So do this.
Is there any property on V?
Convexity property. This is only true for convexity property. It is not true in general. We just saw an example where core is empty. So for every convex game, core will be non-empty, and this is one of the example. Here is another thing which is the motivation for my next part, is that this is one possible allocation. If I change the permutation, if I number the agents in a different way, then my payoff will change, and that would give me another set of allocation. Okay. However, if it is a convex game, it would still lie in the core.
The naming of the agents does not.
But the payoffs will change.
Okay. But the code does not change. Code is invariant.
No.
Because all of these things will lead to a core solution. Even though
Core
there
does
is
not
no-
need not have a unique solution. So core will have multiple solution. What I am saying is, if you change the number, you will get different payoff allocations, which could be completely different from what you got from these numbers. But they will still lie in the core because of the convexity property.
So now, is there a notion of saying this is the best from the code?
Okay, that is Shapley value. Okay, we have done this, we have done this. Again, find the core. I mean, it's easy to do, so I am skipping it. So coming to Sushmita's question, if you have core which has multiple allocation, is there a notion which basically define the best payoff allocation? Okay. So what happened here is that I will it's not exactly from the core, because Shapley value gives something which may not lie, it's just a formula. But what happened here, at least we understand that this marginal contribution is good. The only problem that happened was, because I was changing the permutation, my allocation was completely changing, right. So it may happen that in one permutation I am getting something, in other permutation I am getting something completely different. Okay. So if I could do something, okay, if I can do something about this permutation, then I am through. So I am saying, if my allocation basically capture all possible permutations in some way, if my solution capture all possible permutation in some way, then it makes a reasonable solution.
Yes, because then it's like, doesn't matter which group of people I belong with, my marginal solution, the marginal utility is guaranteed.
Now how will you do that? So you understood the problem. Is the problem clear? So problem is, this particular solution, at least for the convex scheme, was a good solution. However, in the core, if I change the permutation, so if I make second agent here, okay, and first agent here, then the allocation will change, right. Then x2 will be v2, which can be completely different from this, okay, and x1 will be v12 minus v2, right. So the allocation will change whenever I change the permutation, okay. And the question I am asking, in the convex game itself, which allocation should I choose? Ideally, you do not want it to be dependent on the permutation, right.
Define a partial ordering on these allocations.
But then it will still depend on the partial ordering.
Correct.
The solution is extremely simple.
Average.
You average it, okay. You find all possible permutation and choose the allocation which is average, and that is your Shapley value. Nothing. It has a complicated formula, but this is what it is. It's just the average of all permutation of the marginal contributions.
How is it better than just picking one on the core?
Because it's not dependent on the ordering, okay. It's kind of some fairness, right. It doesn't matter where I belong, okay.
On an average, this is my.
On an average, this is my utility.
So we have something better than Shapley value. I mean, are there any disadvantages to Shapley value?
So Shapley value in general has been working really good. There are like computational complexity is the one, because here what you are doing, it's not easy to compute Shapley value, right, because you need to compute the marginal contribution of each and every agent. That means you need to compute all the possible subsets, and then you need to compute all the permutation, you need to take the average, okay. We will skip this is easy, okay. So Shapley value is basically the nice concept which satisfies symmetry, linearity and carrier property. I will describe these, but what I want to do before that, as I said, formula we will see, but essentially intuitively it's nothing but the average of all these allocations, okay. the thing that I want to emphasize is that shapely value is just a value, it is a formula. Therefore, shapely value will always exist, no matter core exists or not. Okay. But for a convex game, shapely value will lie in the core.
Just previously.
This is just nothing but permutation that I wanted to define, which we already know.
Yes. Is it possible for an
Huh?
application which is not in the code but still to attain the shapely value? I mean, that doesn't even make sense.
Yes, because if shapely value will always exist.
It's a value.
It's
So
a value. Yes.
So whether, I mean, it could be attained by a non-core solution also.
It could, but core is not empty.
Yes. Is it possible?
I think it is possible. I think so.
Because that would be a really complicated situation. Like I'm attaining the value, but I'm not in the core.
It could be because I don't know, there is a paper why core is better than shapely values. I am hoping it is true, but I don't know. I need to check this out. Okay, to be honest, I am not so sure.
So for convex game it might
For
not
convex
like-
game, it is in core. That I know.
So,
So what she is asking is, can it happen that non-convex game, can it happen that there is a core which is non-empty and you have a shapely value, but shapely value doesn't belong to the core? That I am not sure.
By average, you mean summation of x at the end, right?
Yeah, but here, no, not n, but all possible permutation. So there will be n factorial permutation.
there was one line that core is convex. So
Huh,
one of those lines. Yes. So core need not be.
that is different. Core is convex means if the two solution concepts are in core, then the convex combination of these two solutions will also be in core.
If such a solution exists, which is in core and not a shapely value, then that solution is better than shapely value, right?
I'm not sure. Let me not remark on this. Let me think on this. Okay. Sorry. Yeah.
I mean, no, right? Because depending on the ordering of the agent, an agent might be doing really well under something, but because it's not part, it does not attain the shapely value. Maybe there's some other ordering in which that agent does really badly.
No, what he is saying is that suppose what you are saying is true. Let's say there is a solution concept which suppose you have a shapely value and there exists, and it is not in the core, and there exists another solution which is in the core.
Yes.
Okay, then what he is saying is, why would you go to the shapely value, why not core?
Correct. So the point is, I wouldn't want to, but the point is, I would, just by looking at the solution, I may not be able to know that I have attained the shapely value, but I'm still not in the core. I mean, okay, depends on the algorithm also. It's like, is it easy to know, check whether I'm in the core?
Yeah, you just need to satisfy all
Those
those
conditions.
properties.
So checking verification of being in the core is easy.
See, according to me, intuitively, okay, shapely value should come in core
You are taking
because
all
the
permutation-
margin, huh?
Because you are taking all the permutation and then calculating shapely value.
No, but the issue is that the the way that it's not so easy. The way I have defined the payoff allocation, okay, this is in the core only for convex game.
We are talking about this one.
No, for convex game I have already told. For a general game we are not sure.
Yeah, I'm also imagining a general game which is hard to given
Exactly.
how the payoff of this thing will look like.
So I need to think about it, but it's a good question. Okay, so but shapely value basically satisfies these three properties which are also good property. Symmetry, which is the primary motivation why we went to shapely value. Symmetry property simply says that whatever value I am getting by being player number 1, I should get the same value by being an arbitrary number. So even if you change the permutation, the shapely value should not change. Okay, so that's symmetry. That means if you relabel, then nothing changes.
The average should not change. That makes sense.
No, not the average. I am just saying that now, you know, shapely value is satisfying these three properties. So you are, so he asked a question, right? That core, if shapely value is different from core, then is shapely value good? So I am saying I don't know the answer to this question, but I know that shapely values satisfy these 3 nice properties.
Okay.
Now it's up to you whether you want these 3 properties or not.
Yeah, so I am saying symmetry makes sense because the definition of shapely value somehow involves in it average.
Yes. So proving that shapely value is a symmetric is not a difficult thing. Okay, intuition is pretty clear. Okay, this is again saying the same thing. I am going slightly faster now. Okay, so linearity says the following. If I have 2 coalitions game with the same number of players, same set of players, the valuation function is V and W respectively. If I consider a new coalition game, which is the convex, which is where the valuation function is coming from the convex combination of V and W, then the allocation that you have will also be the corresponding convex combination. Does it make sense? Okay, again easy to see, it's just a linear combination of the marginal contribution and marginal contribution you are just doing a convex combination, it will satisfy this linearity property. Not very difficult to see that the shapely value will satisfy this property. Okay. The third property says the following. A coalition D is said to be carrier of a coalition game if V of C intersection D is equals to V of C. Let's just do this. Okay, what does it mean? It means that suppose D is a carrier. Okay. So when do you say D is a carrier? When V of C intersection D is always equals to V of C. Okay. Now let us say D is a carrier and suppose you take an agent I which does not belongs to D. Okay. So in this case what should happen? You should see V of I intersection D, which will be V of phi. Okay. This is 0. Okay. And V of C will be V of I. Okay. So what I am doing is, for any valuation function that is given to me, I am trying to find whether there exists a D which satisfy this property for all C. Suppose there exists, it is not guaranteed it will exist. Suppose it exists, then I call such a set D to be carrier, and for all the agents not in the carrier, what I want is that their the Vi will be 0. Okay, the Vi will be 0, and if you take any C which is a subset of n and you take I does not belong to D, then V of C union I will also be equals to V of C. That means I is not contributing anything to any of the set. His own valuation is 0, not only his own valuation is 0, but he is not contributing anything to any other set. Okay. Then if such things happen, it is not necessary it happens, then what carrier axiom says that if these kind of agents exist, they are called the dummy agents and the allocation to these dummy agents should be 0. They are like redundant, they are not adding anything to anything. Okay. And the third, so this is called the third property, and shapely values satisfy the carrier axiom. Okay. Okay. This I have done, this I have done. Yes,
To be a
please.
carrier, the value of the agent also should be 0.
By definition, because you have this property V of C intersection D has to be equals to V of C. No, so to be a carrier, the agents which are not in the carrier should have the valuation 0. Carrier are good people. Carrier is the people who are carrying the entire load on their head. Okay, so the other people are not doing anything.
So if you call a person dummy, his value individually is 0.
Yes. And if this person is added to any set,
It doesn't make any change.
This is the formula of Shapley value. As I said, it's just the average, don't get too much confused. N factorial is basically taking the average. This term is basically saying in how many coalitions C is coming, and this is the marginal contribution. In how many coalition I is coming, and this is the marginal contribution. Again, I will leave it to you. I am extremely hungry, so I will leave it to you to prove that this is nothing but the average. Okay, and that ends my talk. I hope so. Yeah. So, unlike core, Shapley value always exists. Shapley value may not. Acha, I have this. Shapley value may not belong to core. Shapley value of a convex scheme always belong to the core. So, but I don't know the example. I need to think about it. That's all. Thank you very much.